Have you ever found yourself wondering why a spring always seems to snap back to its original length when you stretch it or compress it? In the energy filament theory, the reason behind this isn't some mysterious memory of the spring's original position. Rather, it's the internal energy filaments within the springs that are being twisted and distorted. The energy C inside the spring becomes misaligned and uncomfortable, forcing the spring to return to its most stable, least strained position, its natural length. To better understand this, let's first imagine a neatly coiled headphone wire. Each coil is perfectly arranged and aligned, sitting comfortably side by side. Now, when you stretch and twist it, you're physically elongating the wire. But from the wire's perspective, the loops are no longer aligned neatly, they're forced into awkward angles. Some parts of the wire get stretched too tightly, while others are compressed into tight kinks. This creates what we can think of as energy wrinkles that force the wiring into a more uncomfortable configuration. The wire's internal structure is disrupted, making it feel unnatural. A metal spring behaves in a similar way. However, the difference is that the spring's structure is locked into place on an atomic level. When you stretch the spring, you're forcing the coils to straighten, pulling apart the gaps between them. This results in the local tension or stretch of the spring increasing. If you compress the spring, you're forcing the coils to become too close together, and the energy distribution within the spring is disrupted. The coils then start fighting for space, creating a kind of resistance within the spring and internal "I don't want to be compressed like this" tension. This tension builds up, and the spring enters a state of discomfort. When you release the spring, these tensions are quickly called in, and the spring's internal structure immediately begins to return to its most comfortable, balanced configuration. The spring snaps back to its original shape because the internal forces demand that the spring's energy filaments return to their natural alignment. It's not the spring remembering where it was, but rather the spring returning to the most efficient, best energy state it can attain. This process is a kind of natural compensation for the tension you've introduced. The force you feel when you stretch or compress a spring is simply the spring trying to return to its most natural, least strained form. Just like how a rubber band snaps back when you let go. Now, imagine the spring as a metaphor for energy itself. When you stretch a spring, you're adding energy to the system, just like how work is done in everyday life. The energy is stored within the spring's filaments, just as you're storing tension in the structure itself. When you release it, the energy stored within the spring flows back into the system in a more balanced, natural way. The spring's recoil, the way it snaps back, is the energy within the system seeking equilibrium. This principle is fundamental to understanding how energy behaves at both the microscopic and macroscopic levels. It's not just the spring that follows this principle, everything in the universe does. For example, when you push an object, like a car, across the ground, the energy you use to move it is transferred into the object and into the ground beneath it. In turn, the object moves because the ground provides an equal and opposite force to your push, just like the way the spring pushes back in the opposite direction when you release it. Similarly, when we think about gravity or other forces, we're simply observing this natural tendency for things to return to a state of balance and equilibrium. Gravity, for instance, pulls objects toward the Earth not because of some mystical force, but because the Earth is creating a gravitational slope in the energy sea, a slope that objects naturally move towards to achieve the least energy expensive position. So, when you let go of an object, it doesn't fall because some invisible hand is pushing it down. It falls because the object is moving along this gravitational slope, returning to a state of minimum energy, just like the spring snapping back to its natural length. In essence, what we call force in everyday life is the result of the entire structure of the energy sea around us pushing or pulling to find equilibrium. Whether we feel it as a spring pushing back against us, a car stopping after we apply the brakes, or even the way gravity pulls objects downward. All of these are examples of the energy sea trying to return to a state of minimal tension and maximum efficiency. Every interaction, whether pushing, pulling, or braking, is a negotiation between energy and structure. Whoever changes the terrain, whoever changes the flow, has to pay for it. In the next episode, we will delve deeper into the nature of energy conservation and discuss why energy doesn't simply disappear but always gets transferred or redistributed. Tap follow, share it on New Physics, Clear Universe.